Hi friends, again in our previous lesson we learned sets and numbers, and today we will continue with functions or mappings. So let's start. What is function? A function is often described as a rule which associates with an element in one set and a unique element in another set. So we will give a definition which avoids the undefined term rule. So let it be our first set A, B, and C. And this is our second set. Let it be D, E, and F. Okay. And a function is often described as a rule between A and B. Okay, it associates with an element in set A, a unique element in another set B. Okay, the input is from A, the output is from B. This is a rule. And now let's give a definition in order to clarify. Okay, definition. Let X and Y be into non-empty sets which may be equal. The option A function f from X into Y is a subset of X cross product Y. Cross product means Cartesian product, in other words, with the property that for each X from the first set X, there is precisely one element XY in the subset F. We write F, this is an operator F from X to Y to indicate that F is a function from X into Y. Okay, another definition. The set X is called the domain of the function F. Okay, again, here is our, let me change the color. Okay, here our element A, B, and C. Let me write it clearly here. Okay, A, B, and C. This is X. Let it be X. This is input of the function. We can name it as input, or we can call it domain. This is the main. Wow. And if we link this domain with another set, D, E, and F, and this is range or output. Okay, output or range or image, maybe image. They are all the same. This set X is called the domain of the function, and if xy of f for some function f from x to y, and some x from x, then we call y the image of x under f. Okay, this is y. This set is the image of x under f, and we write y is equal to fx. Okay, and let's continue. So let S be a subset of X. The set Y, which is Y from our set of images, and for some X from S, which is a subset of Y, is called the image of the set S under F from X to Y, and is denoted by Fs. The subset Fx of Y is called the range of F. Okay. Oh, what did I do? S is a subset of X. It may be just A, or let me change the color. Let S be this set. Okay, and here the set Y, which is a subset of Y, let it be D and E, is called the image of the set S. Okay, if we link them, this is the subset of X, which we call S, and this is the subset of Y, and which we denote by Fs. Okay, the subset Fx of Y is called the range. This is called the range. So when Fx is equal to Y, we say that the function f is from X onto Y rather than into Y, and we call f an onto function. Okay, we will show examples for onto functions. Let me clear the drawings. Okay, if for x1, x2 from X, we have fx1 is equal to fx2 only when x1 is equal to x2. Then we call the function fx from Y 1 to 1. And an onto function is also said to be surjective or a surjection. A one-to-one function is also said to be injective or an injection. A function that is both injective and surjective is called bijective or a bijection. So let's show examples for these definitions. Okay, now here you see four functions, okay, four sets. Five sets and four functions between them, four rules between them. Now F1 is one-to-one since no element of B is the image of more than one element of A. So here you see for A, for one input, there is just one output. Okay, you see, here is just one connection, just one X. For one input B, there is just one output. For C, again, there is just one output. You see that for any input, there is just a unique output. And we say that this function is one-to-one, okay? Similarly, F2 is also one-to-one. You see here, one is input. One is input and R is output. Just for one input, here is just one output. For two, we have T, yes, and for three, we have U. For four, we have S. Again, one input, one output. This is also one-to-one function. However, neither f3 nor f4 is one-to-one. Why? Because here for f3, let me change the color. This is input, yes, one input, one output. But V is the output for U also. You see, two inputs, we have one output. For U here and for R, we have just one output, V. And for S, for T, we have again one output, W. So if we have two inputs, one output, we say that this is not one-to-one function, okay? We can show example x square, the function x square. If we put -1, the square of -1 is equal to 1, yes? If we put +1, the square of +1 is also 1, yes? The square of -1, -1 and +1 is 1. So this is just one example. Okay. What about F3 and F4? As far as being onto is concerned, F2 and F3 are both onto functions since every element of C is the image under F2 of some element of P, and every element of D is the image under F3 of some element of C. Okay. Let me clear. You understand the one-to-one function. Now we will clarify the onto function. So what is onto function? How did we find out that it's onto or not? You see, F2. For all the outputs, there is some input from B, okay? The image under F2, it means that every element of C is the image under F2, some element of B, okay? And every element of D is an image under F3, and you see here there is no element that is not an image of any element from C or from B. Look at the difference, please. For F1, here there is an element. You can't find any how can I say, rule. You can't find any rule. 3 is not the image of any element from A, yes? But here we can't find the remaining element. Here also we can't find. But here we find X and Y, which are not images of any element from D, okay? Here we find out 3, that is not image, and here we find out X and Y, that is not image. But in this set, and also in this set, all elements are image of some elements. Can you find what is onto function? Can you understand what is onto function? f2 and f3 are both onto functions. And let's continue. On the other hand, f1 again is not onto, since 3 from B is not the image of f4 of any element of A, and f4 is not onto since x and y is not the image under f4 of any element of D. Okay, let's continue. Two functions here, f and g from x. Look at the picture. Two functions f and g from x into y are equal if and only if fx is equal to gx for all x from x. In this figure, four functions are shown. Yes, if k, that is a function from x to yk, where k is starts from 1 ends to 4. And here k is the index. It should be here. Okay. Okay, let me. Okay, sorry for the telephone call, and we continue. Four functions are illustrated. Each has the main 1, 2, 3, 4, and 5. Okay, these are the domain 1, 2, 3, 4, 5. The domain of the second function is also 1, 2, 3, 4, 5. The domain of f3 is here, and the domain of f4 1, 2, 3, 4, 5. Let's continue. The function f1 has y1, 1, 2, 3, 4, 5, and 6. Okay, the image of f1, the image is 1, 2, 3, 4, 5, and 6. Again here, the image of 1, 2, 3, 4, the image 1, 2, oh no, no. Look, please. There is some mistake. 1, 2, 3 are the images. 4 also is the image, and 6. Okay, 5 is not an image of any element. Okay, 5 is not an image of any element from X. And here 1, 2, 3, 4 are the image. Here 3 is not image, and 6 is not image. What about last one? All the elements are the image. Okay, here 1, 2, 3, 4. All the elements are image of X. And here 1, 2, 4, 5, and 7 are the images. Here 1, 2, 3, 4, 5 are all the elements are the image of X. Okay, we write it in our next slide. Okay, the function f1 has image 1, 2, 3, 4, 5, and 6, as we mentioned. And the function is the subset 1, 3, 2, 3, 3, 4, 4, 1, and 5, 6 of x cross y1 as indicated by arrows given the image of the elements of f of x. You see, for 1 it's 3, 1, 3. This is x and this is y. 2, 3. Okay. 3, 4. 3, 4. And 5, 6. Here is 4, 1. These are the ordered pairs, which first element from X from subset and second element from Y from the image set. Okay. Let's continue. What about function 2, f2? For the 1, we have image 3. For 5, we also have image 3. This is 1, 3, 5, 3, yes, and 2, 2, 3, 1, 4, 4. I don't write all of them. Here, 1, 2, 2, 1. Yes, 1, 2. It's x and this is y. But here for the 2, we have image 1. 3, 4, 4, 7, and 5, 5. Here, 1, 2, 2, 3, 3, 1, 4, 4, we have image 5, and for 5, we have image 4. All these ordered pairs are the result of the cross product between x and y. Yes? As indicated by arrows giving the image of the element of x. The range of f1 is the set f1x is 1, 3, 4, 6. As we mentioned here, the range of f1 is 1, 3, 4, 5, 6. And the other functions may be similarly described. For all four functions, each element of x is the tail of an arrow and of only one arrow, while the elements of y's may be at the head of more than one arrow, or perhaps not at the head of any arrow. If it's not at the head of any arrow, it means that this is not in the set of image. This situation is typical of any function. The elements of y2 and y3, let me annotate. The elements of y2 and y3, okay, y2 and y3 are all the heads of arrows, so the functions f2 and f4 are both onto functions, okay? f2 and f4 are onto functions. Observe that f1 1 is equal to 3, f1 1 is equal to 3, and f1 2 is also equal to 3. Also, f2 1 is equal to 3, f2 5 is also equal to 3. This situation doesn't apply to the functions f3 and f4. Each element of y3 and y4 is at the head of at most one arrow. So the functions f3 and f4 are both one to one. Okay, f3 and f4 are one-to-one functions. There is one input, one output. Okay, Only the function f4 is both one-to-one and onto, because in f4 all the elements are image, there is not remaining element, and for all input there is just one output, so f4 is image for all. F4 is one-to-one, and it's a bijection. Only for the function f4 of the four functions can we simply reverse the directions of the arrows to give another function from a y into x. We will denote this function temporarily by g, which is from y4 to x in full. f4 is let me for f4 here for 1 we have 2 2 3 3 1 4 5 and 5 4. Okay, these are pairs, ordered pairs. Here is f4, ordered pairs. But what about g? G is the inverse. Okay, for 3, look please, let me annotate. Here. Let's find the rule between y4 and x. For 1, we have 3. 1, 3. 2, 1. Yes. 3, 2, 4, 5, and 5, 4. Yes. Can you understand any unclear part? Please, if you have any unclear part, let me know by commenting below. So, we have G. Look, for 1, we have 3. Okay, here. For 2, we have 1. Here. For 3, we have 2. Here. For 5, we have 4 here, and for 4 we have 5 here. The function g is also a bijection and has the characteristic properties like that. G f for x is equal to x for each x from x, and f4 gy is equal to y for each y from y4. We call g the inverse of the function f4 and denoted by f4 to the minus 1. Okay. Definition. For any bijection f from x to y, the inverse function f to the minus 1 from y to x is the function for which f to the minus 1 y is equal to x whenever fx is equal to y, where x is an element of x, the domain, and y is the element of range. It's sometimes useful in other contexts to speak of the inverse of a function when it's one-to-one, but not necessarily onto. This could be applied to the function f3x, f3 from x to y, 3 above. Let's see. Here also. For one input, we have one output. Yes, we can apply the inverse function to f3 also. And let's continue. We can reverse the rows there to give a function h, but the domain of h would only be f3x and not the whole of y3. Yes, because there is a remaining element which is not an image of any number. Yes, here this will not take part in our new function. Okay. And what else? Definition 3. Let f from x to y and let g from y to z be two functions. The composition of f with g is the function g composition f from x to z given by gfx given by this sign, okay, in this form, where x is the element of the domain. Note carefully that the composition gf is only defined when the range of f is a subset of the domain of g. Okay, if the range of f is a subset of the domain of G, we can talk about composition function. Otherwise, we cannot. And doesn't exist when GF does. And even if it does exist, it needn't be equal to GF. Okay, FG and GF differs. For example, consider the function f1 and f4 above. Okay, let me recall. Consider the function f1, okay, and f4. Look at carefully to the image and to the range. F1, f41 is equal to f1, f41. What does it mean? Let me reopen it again. Okay, I reopened the figure again, and we want to find the composition of F1 and F4. So F1 is here, this, F4 is this. F1, F4 is, what is the range of F41? For 1, we have 3, yes, and sorry, F for 1. For 1, we have 2 here. F for 1 is 2. This 2 is the domain of F1. You see, here, F for 1, we find that it's 2, and we replace it by 2. Okay, F1, 2. The answer is 3. You see here, and so on. What about F4, 2? This is 2. F4, 2 is 3. Yes. And what about F1, 3? We have 4. Okay. Now for 2, we find 4. You see here. For 1, our result is 3. For 2, our result is 4. What about 3? For 3, the range is 1, and this is the new domain. For 1, the range is 3. Yes? And here, 3, 3. And also, what about 4? For 4, our result is 5, and for 5 our result is 6. Okay, 4 6 5 1 1 3, and etc. It keeps going. So do you understand? You have any unclear part, please let me know. And there are some other terms which require mention. For a function itself of the general nature given here, we will prefer the terms map and mapping. So instead of function, we can also say map or mapping. The use of the word function will be restricted to the classical sense, in which the domain and range are essentially sets of numbers. These are the traditional real-valued or complex-valued functions of one or more real variables. So the terms functional and operator will be used later for special types of mappings. And these are the review exercises for you. Try to solve it yourself and let me know if you have any unclear parts. Okay, that's all. Thank you for your attention, and if you have any problem with your today's lecture, please let me know. I will explain it again. Thank you and goodbye. See you in the next video.